Recently, 4 astronauts flew around the moon and came home. Artemis 2 proved we can reach it. But reaching the moon and surviving on it are 2 completely different problems. The surface temperature swings over 300 degrees Celsius between day and night. Radiation bombards the ground at 200 times the dose you receive on Earth. Dust clings to everything with an electric charge and shreds machinery at the molecular level. Micrometeorites strike at up to 70 kilometers per second with no atmosphere to stop them. And your own bones start dissolving because gravity is too weak to maintain them. The moon is the closest world to Earth. It is also one of the most violent environments any human has ever tried to enter. If you enjoy deep dives into the real science behind space exploration, consider tapping that like button and subscribing. It genuinely helps the channel grow and lets us keep making content like this. Now, settle in, get yourself comfortable, let's begin. Look up tonight. If the sky is clear and the timing is right, you will see the moon. You have seen it thousands of times. You know its shape. You recognize the dark patches of its Maria, the bright splash of Tycho crater, the soft grey glow that has accompanied every civilization in recorded history. Children draw it in crayon before they can write their own names. Poets have compared it to a lantern, a coin, a watchful eye. It is the only celestial body where you can see surface features with the naked eye, where you can point at a specific dark splotch and say, that is the Sea of Tranquility, that is where Armstrong walked. No other object in the night sky offers that kind of intimacy. It feels close. It feels familiar. It feels like the most obvious next step for a species that has already put 12 people on its surface and just sent 4 more around it. On April 1st, 2026, NASA's Space Launch System rocket lifted off from Kennedy Space Center and pushed the Orion spacecraft carrying Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen toward the moon. 10 days later, Orion splashed down in the Pacific Ocean. The crew set a new record for the farthest distance any human has ever traveled from Earth, surpassing Apollo 13's mark by more than 4,000 miles. They circled the moon at roughly 4,000 miles above its surface, watched an Earthrise from the far side, witnessed a total solar eclipse as the moon passed between them and the sun, and returned safely. Artemis 2 was a triumph. It confirmed that the Orion spacecraft can keep humans alive in deep space. It proved the heat shield can survive re-entry at lunar return velocities. It demonstrated that 53 years after the last Apollo mission, we can still send people to the moon and bring them home. But here is the detail that matters most. They did not land. They did not touch the surface. They did not step outside. They flew past, observed, and came back. And that distinction contains the entire story we are about to explore, because the gap between flying past the moon and living on it is not a small step. It is an abyss. The moon looks close. It is close, astronomically speaking. The average distance between Earth and the moon is approximately 384,400 kilometers. Light crosses that gap in about 1.3 seconds. Radio signals travel the same distance in the same time. When Apollo astronauts spoke to Mission Control, the delay was barely noticeable. Compare that to Mars, where a radio signal takes between 4 and 24 minutes depending on orbital position. Or Jupiter, where communication delays stretch to nearly an hour. The moon is practically next door. A spacecraft travelling at the speeds achieved during Apollo or Artemis can reach it in roughly 3 days. That is a long weekend. You could leave on a Friday and arrive on a Monday. This proximity creates an illusion. It makes the moon feel accessible. It makes a lunar base sound like an engineering project rather than a survival problem. It makes permanent human presence seem like a matter of funding and political will rather than a battle against physics. The illusion is wrong. And the reasons it is wrong begin the moment you consider what the lunar surface actually is. Strip away the romance. Forget the photographs of astronauts bouncing across grey plains. Forget the poetry of Earthrise. Forget the flag and the footprints. Look at the moon as an environment, a place where a human body must function, where machines must operate, where systems must sustain life. What you find is one of the most aggressively hostile surfaces in the inner solar system. Start with the most fundamental problem. The moon has no atmosphere. Not a thin atmosphere, not a wispy atmosphere. For all practical purposes, no atmosphere at all. The lunar exosphere, as scientists technically classify it, contains roughly 100 molecules per cubic centimetre near the surface. Earth's atmosphere at sea level contains approximately 2.5 times 10 to the 19th molecules per cubic centimetre. The difference is not a factor of 10 or 100 or 1,000. It is a factor of roughly 100 quadrillion. The moon's exosphere is so sparse that individual gas molecules travel in ballistic arcs without ever colliding with each other. It is not an atmosphere in any meaningful sense. It is a vacuum decorated with occasional stray atoms of helium, neon, argon, and sodium. This absence defines everything else about the lunar environment. Every other hostile condition on the moon flows from this single fact. No atmosphere means no air pressure. Earth's atmosphere exerts a pressure of approximately 101 kilopascals at sea level. This pressure is what keeps your blood liquid, your lungs inflated, and your bodily fluids from boiling at body temperature. On the moon, the ambient pressure is effectively zero. A human exposed to this vacuum without a pressure suit would lose consciousness within roughly 10 to 15 seconds as the oxygen in their blood depleted. Their bodily fluids would begin to vaporize. Dissolved gases in the blood would form bubbles, a condition called ebulism. Swelling would occur across the body as water vapor expanded beneath the skin. Death would follow within 1 to 2 minutes, not from freezing or from explosion as popular culture sometimes suggests, but from asphyxiation and the cascading failure of biological systems that evolved to operate under atmospheric pressure. This is not speculation. NASA has documented accidental vacuum exposures in ground-based test chambers. In 1966, a technician at the Manned Spacecraft Center in Houston experienced a suit leak during a vacuum chamber test. The pressure dropped to near vacuum. He lost consciousness in about 14 seconds. He was repressurized in roughly 30 seconds and survived, but reported that the last thing he felt before blacking out was the sensation of water boiling on his tongue. That was on Earth, in a controlled facility, with emergency systems standing by. On the moon, there is no ambient pressure to restore. There is no atmosphere waiting outside the airlock to rush in and save you. The vacuum is permanent. It is the default state of the entire world. This also means there is no protection from the sun's unfiltered ultraviolet radiation at the surface level. On Earth, the ozone layer absorbs virtually all of the most dangerous ultraviolet wavelengths before they reach the ground. On the moon, the full spectrum of solar ultraviolet light hits every exposed surface at full intensity. Materials degrade faster, polymers break down, optical coatings on visors and camera lenses deteriorate. Even the pigments in markings and labels fade and crack under relentless ultraviolet bombardment over months and years. Every surface that faces the sun is being chemically attacked by radiation that Earth's atmosphere filters out so efficiently that most people never think about it. No atmosphere also means no breathable gas. This seems obvious, but the implications extend beyond simply carrying oxygen tanks. Earth's atmosphere provides a self-replenishing supply of breathable air across the entire planetary surface. A human standing anywhere on Earth can inhale and survive. On the moon, every molecule of breathable air must be manufactured, stored, recycled, purified, and contained within sealed enclosures. The air supply for a lunar habitat is not like the air supply for a submarine or an aircraft, where the surrounding environment contains oxygen that can be filtered or supplemented. It is a completely closed system. Every breath an astronaut takes consumes oxygen and produces carbon dioxide. Both must be tracked, managed, and balanced continuously. A failure in the carbon dioxide scrubbing system does not mean opening a window. It means a countdown to toxic atmospheric levels inside the habitat. No atmosphere also means no sound. This is not a minor inconvenience. On Earth, sound is a survival tool. You hear a warning shout. You hear a machine grinding before it fails. You hear a leak, a crack, a creak in a structure under stress. On the lunar surface, sound cannot travel between two astronauts standing 5 meters apart unless they use radio communication. If a piece of equipment is failing behind you, you will not hear it. If a fellow crew member is calling for help outside your line of sight, you will not hear them. If a meteorite strikes the habitat wall, the crew inside might feel the vibration through the structure, but the crew outside will perceive nothing at all. This silence is total. It is absolute. It strips away one of the most fundamental sensory channels that humans use to monitor their environment and respond to danger. Every outdoor operation on the moon must compensate for the complete absence of auditory awareness through visual monitoring, radio discipline, and sensor systems that replicate what your ears would normally provide for free. The absence of atmosphere creates another problem that sounds almost philosophical but has devastating physical consequences. There is no weather on the moon, no wind, no rain, no clouds, no convection. This means there is no mechanism for redistributing heat across the surface. On Earth, the atmosphere acts as a thermal blanket. It absorbs solar radiation, circulates warm and cool air, transports heat from the equator toward the poles, and moderates temperature extremes through water vapor, clouds, and ocean atmosphere coupling. The difference between the hottest and coldest temperatures ever recorded on Earth's surface spans roughly 146 degrees Celsius, from roughly -89 in Antarctica to approximately 57 in Death Valley. That range exists across an entire planet with dramatically different climates and geographies. On the Moon, a single location at the equator experiences a temperature swing of approximately 300 degrees Celsius every lunar day. During the daytime, when the sun beats down on the regolith for roughly 14 Earth days straight, equatorial surface temperatures climb to approximately 127 degrees Celsius. That is above the boiling point of water at sea level, hot enough to cause severe burns on contact, hot enough to degrade seals, warp materials, and stress every joint and surface of any structure exposed to it. Then the sun sets, and for the next 14 Earth days, the same surface plunges to approximately -173 degrees Celsius. That is colder than any natural temperature ever recorded on Earth, cold enough to make steel brittle, cold enough to shatter glass, cold enough to freeze carbon dioxide solid. To grasp what that swing means in practical terms, consider that your kitchen oven, at its maximum setting, reaches roughly 260 degrees Celsius. The temperature difference between the lunar day and the lunar night is larger than the difference between your freezer and the hottest setting on your oven. Now imagine a single structure, a single sheet of metal, a single window, a single seal between pressurized air and vacuum, being forced through that entire range every 4 weeks. Not inside a laboratory under controlled conditions, on a surface where no technician can walk outside in shirt sleeves to inspect a crack or tighten a bolt. That is the thermal reality of the Moon. The poles tell an even more extreme story. In the permanently shadowed craters near the lunar South Pole, regions that have not seen sunlight in billions of years, temperatures drop to approximately -233 degrees Celsius. NASA's Diviner Lunar Radiometer on the Lunar Reconnaissance Orbiter measured temperatures within the Hermite crater at the North Pole, reaching approximately -248 degrees Celsius. That is only 25 degrees above absolute zero, among the coldest naturally occurring temperatures measured anywhere in the solar system. These numbers are not abstractions, they are engineering realities. Every material used in a lunar habitat must survive this thermal cycling. Metals expand when heated and contract when cooled. Repeated cycling between 127 and -173 degrees causes thermal fatigue, microscopic cracking that accumulates over time and eventually leads to structural failure. Seals degrade, Lubricants freeze or evaporate depending on the temperature phase. Solar panels must endure the thermal shock of transitioning from extreme heat to extreme cold and back again every 29.5 Earth days. On Earth, engineers design for thermal environments measured in tens of degrees of variation. Cars, bridges, buildings and aircraft operate within a temperature range of perhaps 100 degrees Celsius across their entire service life, and usually far less. Lunar hardware must survive 3 times that range every single month. Not once, not occasionally, every month, for years. Without maintenance crews that can work comfortably in the open air, without a hardware store down the road, without the option of simply replacing a failed component by driving to a warehouse, the thermal environment creates another problem that most people never consider. Heat transfer on the Moon works differently than on Earth. On our planet, heat moves through conduction, convection, and radiation. Convection, the transfer of heat through moving fluids, does enormous work in daily life. It is why a fan cools you down. It is why warm air rises and cold air sinks. It is why your house does not become an oven when you turn on the stove, because air circulates and distributes the heat. On the Moon, convection does not exist outside a habitat. There is no air to circulate. Heat cannot be carried away from a surface by moving gas. This means that thermal management, keeping equipment and habitats at survivable temperatures, depends entirely on conduction and radiation. A piece of equipment in direct sunlight will heat up far faster than it would on Earth because no air carries the heat away. A piece of equipment in shadow will cool down far faster for the same reason. The boundary between sunlight and shadow on the Moon is brutally sharp. Step from shadow into direct sunlight, and the temperature difference can be over 200 degrees Celsius across a distance of centimeters. There is no gradual transition zone. No warm breeze blowing from the sunny side, just an instantaneous thermal cliff. Apollo astronauts experienced this directly. Eugene Cernan, commander of Apollo 17, described how one side of his suit would feel scorching while the other side felt frigid, depending on his orientation to the sun. The Apollo suits used a liquid cooling garment with water circulating through narrow tubes against the skin to manage body temperature. Even with that system, thermal comfort required constant adjustment and awareness of solar angle. And those were short excursions measured in hours, not the days, weeks or months that a lunar base would demand. For an astronaut conducting extended surface operations, this thermal asymmetry is constant. The suit's thermal control system must continuously manage it, pumping heat from the hot side to the cold side, or radiating excess heat through specialized surfaces. A failure in this system does not mean discomfort. It means heat stroke on one side of the body and frostbite on the other. For a habitat, thermal management becomes one of the single largest engineering challenges and energy demands. During the 14-day lunar day, the habitat must reject enormous amounts of solar heat to prevent interior temperatures from climbing to lethal levels. During the 14-day night, it must generate and retain enough heat to prevent freezing while also maintaining power without solar energy. This is not like heating a house in winter or cooling one in summer. It is like doing both, at extreme levels, on a repeating 2-week cycle, with no grid to draw power from, no fuel station to refill from, and no repair technician to call. The lunar night deserves special attention because it represents perhaps the most underestimated challenge in lunar surface operations. 14 Earth days of total darkness. No sunlight means no solar power. Any habitat, rover, or piece of equipment that relies on photovoltaic panels must either shut down for 2 weeks or carry an alternative power source capable of sustaining full operations through the entire night. Batteries alone cannot realistically provide this. The mass of batteries required to power a crewed habitat for 14 days would be enormous, far exceeding what current or near-term launch vehicles could deliver economically. Consider the scale of the problem. A crewed lunar habitat requires power for life support, atmospheric processing, thermal regulation, lighting, communications, water recycling, food preparation, and scientific equipment. Estimates vary, but a minimal crew of 4 would likely require at least 40 to 60 kilowatts of continuous electrical power. Over 14 days, that translates to roughly 13,000 to 20,000 kilowatt hours of stored energy. The best lithium-ion batteries currently available store approximately 250 watt-hours per kilogram. To store 20,000 kilowatt hours would require 80,000 kilograms of batteries, 80 metric tons. That is roughly equivalent to the combined mass of the 4 heaviest modules on the International Space Station. Launching 80 tons of batteries to the lunar surface is not just expensive, it is logistically absurd with current launch infrastructure, and those batteries would need to be replaced after a few hundred charge cycles, meaning fresh batteries would need to arrive regularly for years. Nuclear power systems, specifically radioisotope thermoelectric generators or small fission reactors, offer a potential solution. NASA has been developing the Kilopower project, a small fission reactor designed to produce up to 10 kilowatts of electrical power on planetary surfaces. But these systems have never been operated on the lunar surface. They introduce their own engineering challenges, including radiation shielding for the crew, thermal management for the reactor itself, and the political and logistical complexities of launching nuclear material into space. A crewed habitat would likely need multiple kilopower units operating simultaneously, with redundancy built in for the inevitable maintenance requirements. Each unit must survive the same thermal cycling, dust exposure, and radiation environment that threatens everything else on the surface. The alternative is to locate habitats in regions that receive near-continuous sunlight. Certain elevated areas near the lunar poles, sometimes called peaks of eternal light, receive sunlight for most of the lunar cycle because the moon's rotational axis is nearly perpendicular to the plane of the solar system. These locations could theoretically provide near-constant solar power, but they are small, isolated, and limited in number. Some may be no larger than a few hundred meters across. Building a base on a mountain peak to chase sunlight constrains every other aspect of site selection, including access to water ice, terrain safety, scientific value, and operational flexibility. And even these favored peaks are not truly eternal. They experience brief periods of shadow during certain orbital configurations. A habitat relying solely on solar power at a peak of eternal light would still need battery backup for those dark intervals, and any expansion of operations beyond the peak itself would face the full 14-day-night cycle of the surrounding terrain. The Apollo missions sidestepped nearly all of these problems through a simple strategy. They were short. Brutally short, by the standards of what we now talk about when we discuss lunar bases. Apollo 11 spent approximately 21 hours on the surface. The longest Apollo mission, Apollo 17, lasted about 75 hours on the ground, just over 3 days. During that time, the astronauts operated in a narrow window of the lunar morning, when temperatures were rising but had not yet reached their peak. They carried everything they needed with them. They generated no waste that could not be left behind. They made no attempt to manage the lunar night because they were gone long before it arrived. Every Apollo landing was a sprint. Get in. Do the work. Get out. The astronauts accepted extraordinary risk for a brief duration and then returned to the safety of Earth's atmosphere, magnetic field, and gravitational embrace. That approach worked for exploration. It does not work for habitation. The current Artemis timeline reveals how seriously NASA takes this distinction. Artemis 2, the mission that just returned on April 10th, was a flyby, no landing. The next mission, Artemis 3, is planned for mid-2027 and will not land on the Moon either. It will test lander rendezvous and docking procedures in Earth orbit, practicing the choreography that a future landing mission will require. The first crewed landing under the Artemis program, now designated Artemis 4, is targeted for early 2028. If it succeeds, 2 astronauts will spend approximately 1 week on the surface near the lunar South Pole. 1 week. 6 years of program development, tens of billions of dollars in investment, and the result is a surface stay roughly comparable in duration to the longest Apollo mission. That is not a criticism of the program. It is an acknowledgement of the problem. Even with 21st century technology, even with reusable landers and advanced spacesuits, and decades of accumulated engineering knowledge, a 1-week surface stay represents the current limit of what can be responsibly attempted. The Lunar Gateway Station, which was originally planned to serve as an orbital outpost supporting surface operations, was cancelled in March 2026. The path from a 1-week visit to a permanent base remains undefined, because the engineering challenges separating those two goals are not incremental, they are transformational. The difference between a 3-day visit and a 3-year stay is not simply a matter of multiplying consumables by a larger number. It is a qualitative shift in the nature of the problem. A 3-day mission can tolerate single-point failures because the crew can abort and return home. A 3-year base cannot tolerate single-point failures because there is no rapid return option for most emergency scenarios. A 3-day mission can carry all its water, food, and air from Earth. A 3-year base must either receive regular resupply launches, each costing hundreds of millions of dollars, or manufacture essential resources from local materials, a capability that has never been demonstrated at operational scale on any world other than Earth. A 3-day mission can ignore long-term material degradation. A 3-year base must contend with thermal cycling, radiation damage, dust accumulation, micrometeorite erosion, and the gradual failure of seals, bearings, electronics, and structural components in an environment that attacks every surface from every direction simultaneously. When something breaks, the crew fixes it themselves or it stays broken. Every component must either last for the duration, be repairable with tools and materials brought from Earth, or be manufacturable on-site from lunar resources using equipment that itself must survive the same hostile environment. This is the core deception of the Moon's proximity. Because it is close, because we have been there before, because we can see it from our backyards, because Artemis II just flew around it and came home safely, the Moon feels achievable. It feels like a destination, a place you can go to and then be at. But being at the Moon, in the sense of remaining there and staying alive, is not a matter of arrival. It is a matter of continuous, unrelenting, active survival against an environment that is trying to kill you through at least half a dozen independent mechanisms simultaneously. Think about what we have established so far. A human being on the lunar surface cannot breathe, cannot hear anything outside their suit, cannot survive 15 seconds of direct exposure, cannot touch the ground during the day without being burned, cannot remain outside during the night without freezing, cannot generate solar power for 2 weeks out of every 4, and cannot simply walk to a different location to escape any of these conditions, because they are the same everywhere on the entire surface of the Moon. There is no temperate zone, there is no sheltered valley, the hostility is total and uniform, and we have only discussed vacuum and temperature, the visible threats, the ones you can understand by looking at the Moon through a telescope and noting the obvious absence of blue sky and white clouds. What comes next is worse, the threats that you cannot see, the ones that operate on timescales longer than a 3-day visit, the ones that Apollo never had to confront because the astronauts were not there long enough to encounter them. Radiation pouring through the surface from every direction in the galaxy, dust so fine and so aggressive that it destroys equipment at the molecular level, and tiny fragments of rock travelling faster than any bullet ever fired on Earth, slamming into every exposed surface with no warning and no defense except the walls you brought with you. The Moon is not a destination. It is a siege, and the siege has barely begun. The vacuum will kill you in seconds. The temperature will kill you in minutes. But radiation will kill you in a way that is far more insidious, because you will never feel it happening. You will not see it. You will not hear it. You will not smell it, or taste it, or sense it in any way that evolution equipped you to detect. It will pass through the walls of your habitat, through the fabric of your spacesuit, through your skin, through your muscles, and into the nuclei of your cells, where it will silently break the molecular bonds that hold your DNA together. And on the Moon, this is happening every second of every day, from every direction, without pause, without mercy, and without any natural barrier to slow it down. On Earth, you are protected from cosmic radiation by two enormous shields that most people never think about. The first is Earth's magnetic field, the magnetosphere, generated by the churning liquid iron core thousands of kilometers beneath your feet. This field extends tens of thousands of kilometers into space, deflecting the vast majority of charged particles streaming in from the Sun and from deep space. Without the magnetosphere, the solar wind and galactic cosmic rays would strip away the atmosphere over geological time and irradiate the surface continuously. The second shield is the atmosphere itself. It provides protection equivalent to roughly 10 meters of water stacked above your head. High-energy particles that make it past the magnetic field collide with atmospheric molecules and lose energy through cascading secondary interactions, so that by the time they reach the ground, the radiation dose is negligible. The combination of these two shields reduces the cosmic radiation dose at sea level to approximately 0.39 millisieverts per year. That is your baseline. That is what normal feels like. The Moon has neither of these shields. It has no global magnetic field. It lost whatever dynamo it once possessed billions of years ago, when its small iron core cooled and solidified. There are localized patches of remnant magnetism in the crust, fossil fields from an ancient era, but they are weak, scattered, and far too small to provide meaningful protection for a habitat or a crew. And it has, as we established, effectively no atmosphere. The exosphere is so thin that it provides zero shielding against incoming particles. This means that the lunar surface is exposed to the full, unfiltered flux of two distinct radiation sources that together create a continuous and inescapable hazard. The first source is galactic cosmic radiation. These are high-energy particles, primarily protons but also heavier nuclei including helium, carbon, iron, and other elements that originate outside the solar system. They are produced by supernovae, neutron star collisions, and other violent astrophysical events scattered across the galaxy. These particles have been accelerated to enormous energies, some approaching the speed of light, and they travel in all directions through interstellar space. When they reach the inner solar system, the Sun's magnetic field provides some deflection, which is why galactic cosmic ray intensity varies with the 11-year solar cycle. During solar maximum, when the Sun's magnetic field is strongest and most turbulent, fewer galactic cosmic rays penetrate to the inner solar system. During solar minimum, when the field is quieter, more get through. But in both cases, a significant flux reaches the Moon. The second source is the Sun itself. Solar energetic particles are bursts of high-energy protons and heavier ions, ejected during solar flares and coronal mass ejections. Unlike galactic cosmic rays, which provide a steady background, solar energetic particle events are episodic and unpredictable. A solar flare can erupt with no more than minutes of warning from space weather monitoring systems. The Sun provides no schedule. There is no season for solar storms. They can occur at any point in the solar cycle, though they are more frequent during solar maximum. When a major event occurs, the flux of high-energy particles at the lunar surface can spike by orders of magnitude within hours. During a major solar energetic particle event, an unshielded astronaut on the lunar surface could receive a radiation dose large enough to cause acute radiation sickness, including nausea, vomiting, immune suppression, and at the extreme end, death. This is not a theoretical risk. The October 1989 solar storm delivered a radiation dose to the unshielded lunar surface estimated at more than 8 times the dose received by plant workers during the Chernobyl nuclear disaster. Had Apollo astronauts been on the surface during that event, they would have faced a medical emergency with no hospital, no treatment facility, and a 3-day journey home. For a lunar base, this means that a radiation storm shelter must be accessible within minutes of a solar event warning, not hours, minutes. Astronauts conducting surface excursions must have a protocol for reaching shielded protection before the particle flux reaches dangerous levels. This constraint shapes everything about surface operations. from how far crews can travel, to how long they can remain outside, to how the base is architecturally configured. Every rover must carry emergency shielding or be within sprint distance of a protected structure. The sun can turn from a benign light source into a lethal particle cannon without warning, and on the moon there is nowhere outdoors to hide. The numbers on the continuous background exposure are sobering enough. In 2019, China's Chang'e 4 lander became the first mission to directly measure the radiation dose rate on the lunar surface using its Lunar Lander Neutron and Dosimetry instrument. The measurement came back at approximately 60 microsieverts per hour. To put that in perspective, the average radiation dose rate on Earth's surface is roughly 0.3 microsieverts per hour. The lunar surface reading was about 200 times higher. It was also approximately 2.6 times higher than the dose rate measured aboard the International Space Station, which orbits within the protective envelope of Earth's magnetosphere at an altitude of roughly 400 kilometers. One day on the moon delivers a radiation dose roughly equivalent to receiving a full-body computed tomography scan. Not once a year, not once a month, every single day you remain on the surface. Over a full year, the accumulated dose from galactic cosmic rays alone reaches approximately 110 millisieverts during solar maximum and roughly 380 millisieverts during solar minimum. NASA's current career dose limit for astronauts is designed to keep the risk of exposure-induced death from cancer below 3%. Since 2022, the limit has been set at 600 millisieverts over an entire career, applied universally regardless of age or sex. A single year on the lunar surface during solar minimum could consume nearly 2/3 of an astronaut's entire career radiation allowance. 2 years could exceed it. And that is assuming no solar energetic particle events occur during that period, which is statistically unlikely over a multi-year stay. The biological effects of this exposure are not confined to cancer risk. Research into the effects of galactic cosmic rays, particularly the heavy nuclei known as HZE particles, which stands for high atomic number and high energy, has revealed damage pathways that do not apply to the types of radiation commonly studied on Earth. When an HZE particle passes through living tissue, it does not simply deposit energy along a thin track the way a medical X-ray does. It creates a column of ionization that can be tens of nanometers wide, destroying every molecule in its path. Cells along the track are killed outright. Cells adjacent to the track receive secondary radiation from the ionization cascade and can sustain DNA damage that is far more difficult for the body's repair mechanisms to fix than the damage caused by low energy. Radiation. This type of damage is called clustered DNA damage, and it has been shown in laboratory studies to be more mutagenic and harder to repair than simple single-strand or double-strand breaks. Animal studies conducted by NASA and other agencies have demonstrated that exposure to simulated galactic cosmic ray environments can cause measurable cognitive impairment. Mice exposed to HZE particle radiation showed increased inflammation in the brain, reduced density of dendritic spines, the tiny protrusions on neurons that form synaptic connections, and deficits in learning and memory that persisted for months after exposure. Whether these results translate directly to humans is uncertain, because the exposures used in some studies were higher than what astronauts would actually receive, and the human brain may respond differently than that of a mouse. But the results are concerning enough that NASA considers central nervous system effects a significant research priority for long-duration missions beyond the magnetosphere. Shielding against this radiation is possible, but it is a mass problem. Radiation shielding works by placing material between the radiation source and the crew, forcing incoming particles to collide with atoms in the shielding and lose energy before reaching the habitat interior. The effectiveness of shielding depends on the material's density and composition. Hydrogen-rich materials like water and polyethylene are among the most effective per unit mass, because hydrogen nuclei are similar in mass to incoming protons and absorb energy efficiently in collisions. But even with optimal materials, meaningful reduction of galactic cosmic ray exposure requires substantial thickness. Studies using NASA radiation transport models have shown that meaningful dose reduction requires burying a habitat under meters of regolith, a significant engineering operation requiring the excavation and placement of thousands of tons of material over the entire surface of a pressurized structure, on a world where every piece of excavation equipment must itself be shipped from Earth or manufactured locally from materials that have never been processed at scale. And here is the catch that makes lunar radiation shielding fundamentally different from radiation protection on Earth or even in low Earth orbit. Galactic cosmic rays come from every direction. There is no single source you can point a shield at. On the International Space Station, Earth itself blocks roughly half the sky, which significantly reduces the total flux. On the Moon, the ground blocks the lower hemisphere, but the entire upper hemisphere is exposed. A habitat must be shielded from above and from all sides simultaneously. Only burial beneath the regolith provides full coverage, which is why some proposals envision building habitats inside lava tubes, ancient subsurface voids that could provide natural shielding from multiple threats simultaneously. Whether these structures are actually usable remains an open question. The radiation problem on the Moon is not a binary hazard. It is not a single event that either kills you or does not. It is a slow, cumulative degradation of biological systems that accelerates with every day of exposure. Unlike a wound or an infection, radiation damage does not announce itself through pain. A crew member accumulating a dangerous dose feels no different from one at safe levels. The damage manifests years or decades later as elevated cancer rates, cataracts, cardiovascular disease, or cognitive decline. For a 1-week visit, the dose is manageable. For a 1-year stay, it becomes a career-limiting exposure. For a 5-year residence, it enters territory where long-term health consequences are probable. And for the kind of permanent settlement that popular imagination envisions, radiation represents a chronic, generational health burden that requires either massive shielding infrastructure or a fundamental change in how long individuals can remain on the surface. The Moon does not care how ambitious your plans are. Physics sets the terms. The second invisible threat is already waiting on the ground before you arrive. Lunar dust is not like any dust you have ever encountered on Earth. It is not powdered rock in the way that desert sand is powdered rock. It has not been shaped by wind or water, or the endless geological recycling that rounds and smooths terrestrial particles over millions of years. The Moon has no wind, it has no water, it has no tectonic activity to churn and reshape its surface layer. Instead, the lunar regolith has been created by a single dominant process, operating continuously for over 4 billion years, the ceaseless bombardment of the surface by micrometeorites. Every square centimetre of the Moon has been struck countless times. The entire visible landscape is the accumulated product of this relentless impact gardening. When a micrometeorite strikes the lunar surface at speeds of tens of kilometres per second, the impact generates enormous local temperatures, thousands of degrees, that melt and shatter the surrounding rock. The result is a layer of fine particles called regolith that blankets the entire Moon to a depth of several meters in younger regions and up to 15 meters or more in older terrain. These particles are angular, jagged, and sharp. They've never been tumbled by a river or abraded by wind. Every edge that formed during the impact that created them remains intact. Under an electron microscope, lunar dust particles look like tiny shards of broken glass, covered in even tinier glass beads formed when molten rock solidified in the vacuum. Many particles contain embedded fragments of metallic iron created by the reduction of iron-bearing minerals during impact melting, a process called agglutination. These iron-rich, glass-welded aggregates are unique to airless bodies and contribute to the dust's unusual magnetic and electrostatic behavior. This shape is the first problem. Angular particles are far more abrasive than rounded ones. When lunar dust comes into contact with a surface, it scratches, gouges, and scores the material far more aggressively than terrestrial dust of comparable size. Apollo astronauts discovered this immediately. After just a few hours of surface activity, the dust had scratched their visor coatings, abraded the outer layers of their spacesuits, and worked its way into joints and seals that were designed to be dust-resistant. Harrison Schmitt, the geologist on Apollo 17, reported that the dust wore through 3 layers of Kevlar-like material on his boots during just 22 hours of surface excursions. 3 layers. In less than a day. Imagine what that abrasion rate means for equipment intended to operate for months or years. The second problem is electrostatic charge. On Earth, dust particles interact with water vapor and atmospheric molecules, which dissipate electrical charge and prevent particles from clinging aggressively to surfaces. On the Moon, the vacuum eliminates this mechanism entirely. Instead, the opposite happens. Solar ultraviolet light and the solar wind continuously strip electrons from dust particles on the sunlit side of the Moon, giving them a net positive charge. On the night side, the dust acquires a negative charge from the electron component of the solar wind that wraps around the terminator. These charges cause dust to cling to virtually every surface it contacts with remarkable tenacity. Apollo astronauts could not brush it off their suits. They could not blow it off because there was no air to blow. They could not shake it loose because the electrostatic attraction held particles against fabric, metal, and glass with a grip that mechanical agitation could not overcome. When the astronauts returned to the lunar module and repressurized the cabin, the dust that had accumulated on their suits became airborne in the confined interior. Every Apollo crew that walked on the surface reported respiratory irritation. Sneezing, nasal congestion, sore throats, and eye irritation were universal. Harrison Schmitt described symptoms resembling severe hay fever that lasted for hours. The cabin of the lunar module smelled, according to multiple crew members, like burnt gunpowder. All 12 people who walked on the Moon experienced these symptoms. All 12, and their total time outside the lunar module ranged from approximately 2.5 hours for Apollo 11 to about 22 hours for Apollo 17. These were exposures measured in hours, inside a spacecraft cabin where the dust had been tracked in on suits and then disturbed during repressurization. A lunar base where crew members conduct regular surface excursions over weeks, months, or years would face dust contamination on an entirely different scale. Recent research has added nuance to the toxicity picture. A 2025 study from the University of Technology, Sydney, tested new generation lunar dust simulants against human lung cells in the laboratory and compared the results to the effects of urban air pollution collected from a busy street. The researchers found that while lunar dust acts as a physical irritant due to its sharp, abrasive particle geometry, it did not cause the severe cellular inflammation or oxidative stress triggered by Earth-based particulate pollution. This is somewhat reassuring for acute exposure scenarios, but the researchers and NASA alike emphasize that the long-term effects of chronic low-dose inhalation remain unknown, because no human has ever been exposed to real lunar dust for more than a few hours, and simulants, no matter how carefully engineered, may not perfectly replicate the chemical reactivity of dust that has been bathed in solar wind and ultraviolet radiation for billions of years in a hard vacuum. The particles on the Moon carry unsatisfied chemical bonds on their surfaces, bonds that were broken during impact events and never had the opportunity to react with oxygen or water because neither exists on the lunar surface. When these reactive particles encounter the moist lining of a human lung, they may behave differently than a simulant whose surfaces have already reacted with terrestrial air. Beyond the biological hazard, lunar dust is an engineering nightmare. It infiltrates mechanisms, abrades seals, scratches optical surfaces, degrades thermal coatings, clogs filters, contaminates connectors, and works into bearing surfaces where it accelerates wear. During Apollo, dust caused zipper failures, scratched camera lenses, eroded suit joints, and interfered with sample container seals. These were problems encountered during the shortest possible surface operations with equipment that would never be reused. For a lunar base, every seal, joint, optical window, and moving component must resist or exclude dust continuously for the entire operational lifetime of the facility. Any failure of dust mitigation becomes a cascading maintenance problem in an environment where maintenance itself is constrained by the same hostile conditions that caused the failure. NASA is developing mitigation technologies. Electrodynamic dust shields use oscillating electric fields to repel charged particles from surfaces. Specialized coatings are being tested that reduce dust adhesion. Advanced airlock designs aim to minimize the amount of dust brought into habitable volumes. But none of these technologies have been validated on the actual lunar surface under real operational conditions. They exist in laboratories and test chambers on Earth, where the environment cooperates in ways the Moon never will. The third invisible threat comes from above, and it arrives at speeds that make rifle bullets look stationary. The Moon is bombarded continuously by micrometeorites, tiny fragments of cometary and asteroidal material that orbit the Sun and intersect the Moon's path through space. On Earth, these particles enter the atmosphere at speeds ranging from 11 to 72 kilometers per second and burn up harmlessly as meteors, the shooting stars you see on a clear night. The atmosphere acts as a shield, converting kinetic energy into heat and light high above the ground. Virtually no micrometeorite smaller than a few millimeters in diameter survives to reach Earth's surface. The Moon has no such shield. Every particle that approaches the lunar surface reaches it at full velocity. A grain of dust weighing 1/1,000,000th of a gram, invisible to the naked eye, strikes the surface at perhaps 20 kilometers per second. At that velocity, even a microscopic particle carries enough kinetic energy to crater metal, pit glass, and puncture thin materials. The kinetic energy of a moving object scales with the square of its velocity. A particle traveling at 20 kilometers per second has 400 times the kinetic energy of the same particle traveling at 1 kilometer per second. These are not gentle collisions. They are hypervelocity impacts that generate localized temperatures of thousands of degrees at the point of contact, briefly creating conditions hot enough to melt and vaporize both the impactor and the target material. A 2025 analysis led by Daniel Yahalomi, using NASA's meteoroid engineering model, calculated the expected impact rates for a hypothetical lunar base with an exposed surface area comparable to the International Space Station. The results were striking. Between 15,000 and 23,000 micrometeorite impacts per year from particles ranging from 1/1,000,000th of a gram to 10 grams. That translates to roughly 40 to 60 impacts per day on a structure the size of the station. Most of these impactors are microscopic, too small to penetrate structural walls but large enough to erode surface coatings, pit windows, and degrade solar panels over time. Larger particles, though rarer, carry substantially more energy. A 10-gram impactor traveling at 20 kilometers per second delivers the kinetic energy equivalent of roughly a stick of dynamite. The study found that impact rates vary by location on the Moon, with the lowest bombardment occurring at the lunar poles and the highest near the sub-Earth longitude. The variation is roughly a factor of 1.6 between the most and least exposed regions. This is welcome news for Artemis planners, since NASA has targeted the South Pole for its initial base site. But even at the poles, the bombardment is relentless. It never stops. It cannot be predicted at the individual event level, and it accumulates. Micrometeorite impacts create a secondary hazard that is unique to airless bodies. When a high-velocity particle strikes the lunar surface near a habitat, the impact ejects a cone of secondary debris, tiny fragments of regolith launched at high speed by the energy of the collision. These secondary particles travel on ballistic trajectories in the vacuum, unimpeded by air resistance, and can strike surfaces at distances far from the original impact site. A micrometeorite that hits the ground 10 meters from a habitat could launch secondary fragments that pepper the habitat wall, the solar panels, the communication antenna, and any equipment or personnel in the area. The habitat itself does not need to be the direct target. The ground around it becomes a source of continuous secondary projectile generation. This means that every exposed surface on the Moon is under constant erosion. Solar panels lose efficiency as their cover glass accumulates microscopic craters. One study estimated that unprotected solar cell cover glass could lose several % of its transmittance within the first year of exposure, directly reducing power output at a time when every watt matters for survival. Thermal coatings degrade as impacts alter their reflective properties, pushing thermal management systems toward their design limits. Optical instruments, cameras, sensors, and windows all suffer progressive damage. Spacesuits worn during surface operations are struck by micrometeorites and secondary ejecta with every excursion. Over weeks and months, this bombardment weakens materials that were engineered to specific performance tolerances on Earth. Designing for this environment requires a fundamentally different engineering philosophy than designing for Earth or even for low Earth orbit. In low orbit, the International Space Station faces a micrometeorite and orbital debris environment, but the station's Whipple shields, layered aluminium and Kevlar barriers designed to disrupt incoming particles before they reach the pressure hull, have proven effective for that threat level. On the Moon, the bombardment is constant, multi-directional, and accompanied by the secondary ejecta problem that orbital facilities never face. Shielding strategies must account not only for direct impacts from above, but for fragments launched from the surface at every angle. These three invisible threats, radiation, dust, and micrometeorites, share a common characteristic that distinguishes them from the vacuum and temperature hazards discussed earlier. They are cumulative. A 1-week exposure to any of them is survivable with current technology. A 1-month exposure introduces measurable degradation. A 1-year exposure creates serious engineering and biological challenges. A 5-year exposure may exceed the design margins of any system currently under development. Each of these threats is manageable in isolation with sufficient mass, power, and maintenance capability. But they do not arrive in isolation. They arrive simultaneously, continuously, and on top of each other, compounding the demands on every system designed to keep humans alive. And lurking beneath all of these external threats is one more hazard that the Moon inflicts on the human body, not from outside, but from within. The Moon's gravity is too weak to sustain the biological systems that evolved under Earth's gravitational load. Your bones, your muscles, your cardiovascular system, your vestibular balance, your immune function, all of them depend on the constant downward pull you have felt every moment of your life. On the Moon, that pull is reduced to 1/6 of what your body expects, and for extended stays, the consequences of that reduction are only beginning to be understood. You can build walls against the vacuum. You can engineer thermal systems to survive the temperature swings. You can bury a habitat under regolith to block radiation. You can design airlocks and dust mitigation systems to keep the regolith out of your lungs. You can armor surfaces against micrometeorites. Every external threat the Moon presents can, in principle, be met with a corresponding engineering solution. But there is one threat you cannot engineer around, because it comes from inside your own body. And the Moon makes it worse simply by being what it is. The Moon's surface gravity is approximately 1.625 meters per second squared. That is roughly 1/6 of Earth's gravitational acceleration of 9.8 meters per second squared. When you see footage of Apollo astronauts bouncing across the lunar surface in their spacesuits, that bouncing is not performance, it is physics. An astronaut who weighs 90 kilograms on Earth weighs 15 kilograms on the Moon. A tool that feels heavy in a terrestrial workshop feels almost weightless. Movement becomes easier. Lifting becomes trivial. Jumping becomes effortless. It looks like fun. It looks like freedom. It is neither. It is a slow-motion crisis that begins the moment you arrive and never stops accelerating as long as you remain. The human body is not a static machine. It is an adaptive system that continuously remodels itself in response to the forces acting on it. Your bones are not inert scaffolding. They are living tissue in a constant state of renovation. Specialized cells called osteoblasts build new bone matrix, while another type called osteoclasts break down old or damaged bone tissue. On Earth, these two processes exist in a dynamic equilibrium maintained by the mechanical loading that gravity provides. Every step you take, every time you stand up, every time you lift an object or simply hold your body upright against the downward pull, your skeletal system registers the stress and responds by maintaining sufficient bone density to bear it. This is not a passive process. It is an active, energy-intensive biological program that your body runs continuously because 4 billion years of evolution on a planet with one full gravity made it essential for survival. Remove the loading and the program changes. In microgravity, where there is no downward pull at all, astronauts on the International Space Station lose approximately 1% of their bone mineral density per month in weight-bearing bones like the hip, spine, and heel. That rate is roughly 10 times faster than the bone loss experienced by a postmenopausal woman with osteoporosis on Earth. After 6 months aboard the station, astronauts can lose 5 to 6% of their hip bone density. After a year, the loss reaches levels where fracture risk becomes clinically significant, and recovery after returning to Earth is slow. Studies of long-duration station crew members have shown that it can take 3 to 4 years to recover the bone density lost during a single year in space, and some astronauts never fully recover. The bone that regrows is structurally different, less organized, potentially weaker than the original. Astronauts aboard the station exercise for approximately 2 hours every day using resistive devices and a treadmill strapped to their bodies with bungee cords. This intensive daily regimen slows the rate of loss, but does not stop it entirely. The body's skeletal remodeling program is calibrated to detect mechanical loading and respond accordingly. And 2 hours of exercise per day cannot replicate the 24-hour gravitational stimulus that Earth provides simply by existing beneath your feet. But here is the critical question for lunar habitation, and it is a question that nobody can definitively answer. What happens in 1/6 gravity? Not zero gravity. Not full gravity. The intermediate condition that the Moon provides. Is 1/6 of Earth's gravitational pull enough to maintain skeletal integrity over months and years? The honest answer is that we do not know. No human being has ever lived in 1/6 gravity for more than approximately 3 days, and those Apollo astronauts were far too busy conducting surface operations to serve as controlled subjects in a bone density study. The data simply does not exist. The closest we have come to answering this question involves mouse experiments conducted by the Japan Aerospace Exploration Agency aboard the International Space Station. Using a device called the Multiple Artificial Gravity Research System, or MARS, researchers housed mice at 3 gravitational levels: microgravity, simulated lunar gravity at 1/6 g, and simulated Earth gravity at 1 g, for approximately 35 days. The results, published between 2023 and 2024, were mixed. On the encouraging side, lunar gravity appeared sufficient to prevent the gross muscle atrophy that occurred in the microgravity group. The soleus muscles of the lunar gravity mice did not shrink the way the muscles of the zero-gravity mice did. The connective tissues between muscle and bone appeared to strengthen in response to even the partial gravitational load. But the news was not all good. Lunar gravity failed to prevent a phenomenon called slow-to-fast myofiber transition. Skeletal muscle contains 2 main types of fibers: slow-twitch fibers optimized for sustained endurance activity, like standing and walking, and fast-twitch fibers optimized for short bursts of power like sprinting and jumping. On Earth, the constant work of supporting your body against gravity maintains a healthy ratio of slow-twitch to fast-twitch fibers in your postural and weight-bearing muscles. In microgravity, muscles shift toward fast-twitch dominance because the sustained loading that maintains slow-twitch fibers disappears. The JAXA experiment showed that this shift also occurred in the lunar gravity mice. 1/6 g was not enough gravitational stimulus to prevent it. What does this mean for humans? If the same pattern holds, astronauts living on the Moon for extended periods might retain muscle mass but lose muscle endurance. Their legs might look normal but fatigue far faster during sustained activity. Walking, climbing, carrying equipment, performing the physical work of maintaining a lunar base, all of it could become progressively more exhausting as the slow-twitch fibers that handle endurance tasks convert to fast-twitch fibers suited for brief explosive movements. This would not be immediately dangerous, but over months and years it would erode the physical capability of the crew and compromise their ability to perform emergency operations that require sustained effort. Bone tells a potentially darker story. The same JAXA experiments showed that microgravity caused significant upregulation of osteoclast activity, the cells that break down bone, while suppressing osteoblast activity, the cells that build it. Under artificial Earth gravity aboard the station, these changes were mostly reversed. Under lunar gravity, the reversal was partial. The bone remodeling balance shifted back toward normal, but not all the way. Markers of bone resorption were still elevated compared to the Earth gravity control group. If this pattern translates to humans, astronauts on the Moon might experience a slower rate of bone loss than astronauts in zero gravity, but they might still lose bone at a rate substantially higher than they would on Earth. Over a 1-year stay, that could mean a clinically meaningful reduction in bone density. Over a 5-year stay, it could mean osteoporotic levels of bone fragility in otherwise healthy adults. And bone loss is not the only concern. The cardiovascular system also adapts to gravitational loading. On Earth, your heart works continuously against gravity to pump blood from your feet back up to your brain. This sustained workload maintains cardiac muscle mass and vascular tone. In microgravity, the heart no longer fights gravity. Blood redistributes from the legs toward the head and chest. The heart remodels, becoming slightly more spherical and losing mass it no longer needs. Blood volume decreases because the body interprets the fluid shift as an excess and begins excreting water and electrolytes. Astronauts returning from space frequently experience orthostatic intolerance, meaning they feel dizzy or faint when standing, because their cardiovascular system has detuned itself from Earth's gravity. In 1/6 gravity, the heart still has to work, but only against 1/6 of the resistance it evolved to handle. Whether this reduced workload is enough to prevent cardiovascular deconditioning is unknown. The Apollo astronauts were not monitored for these effects because their stays were too short and the available medical instrumentation too limited. The ISS provides data on microgravity effects, but there is no space station operating at lunar gravity levels for comparison. The entire range between 0G and 1G is essentially a medical black box with data points only at the two extremes. And the consequences of cardiovascular deconditioning on the Moon would be more immediately dangerous than on the ISS, because crew members must perform physical work on the surface, including operating heavy equipment, conducting geological surveys, and responding to emergencies that could require sustained exertion at a level that a deconditioned heart and vascular system may be unable to support. The immune system adds another layer of uncertainty. Research aboard the International Space Station has documented that microgravity alters immune function in multiple ways. Latent viruses like Epstein-Barr and varicella zoster reactivate more frequently in astronauts during spaceflight. T-cell function changes. Cytokine profiles shift. Inflammatory responses are altered in ways that could either enhance or suppress the body's ability to fight pathogens, depending on the type of immune challenge. Wound healing slows, a finding confirmed in both human observations and animal studies. Whether these effects occur at 1/6 gravity, and to what degree, is unknown. But a suppressed or dysregulated immune system on the Moon would be particularly dangerous because the isolated, confined environment of a lunar habitat is exactly the kind of setting where infectious disease can spread rapidly among a small crew with no access to a hospital, no possibility of patient evacuation within less than 3 days, and no fresh medical supplies beyond what the base already carries. The vestibular system, the sensory apparatus in your inner ear that governs balance and spatial orientation, also depends on gravity for calibration. Astronauts arriving on the station experience days to weeks of adaptation sickness, as their vestibular system adjusts to the absence of a consistent gravitational reference. On the Moon, the vestibular system would need to recalibrate to a weaker but still present gravitational field. How quickly and completely this adaptation occurs is poorly understood. If adaptation is incomplete, crew members might experience persistent disorientation, clumsiness, or impaired spatial judgment. all of which increase the risk of accidents in an environment where even a minor injury could become life-threatening. There is a deeper problem embedded in all of this medical uncertainty, and it has to do with the fundamental difference between what we know and what we need to know. Every piece of data we have about human physiology in reduced gravity comes from either zero gravity or full gravity. We have decades of data from the International Space Station and its predecessors on how the body responds to weightlessness. We have centuries of medical knowledge about how the body functions on Earth. What we do not have is a single data point for any gravitational level in between these two extremes derived from human subjects over durations longer than a few days. The entire spectrum from 0 to 1G is medically uncharted. This means that every estimate of health effects at lunar gravity is an interpolation. We are drawing a line between two known points and guessing where the unknown values fall. But biological systems are not linear. They do not always respond to stimuli in neat proportional increments. It is entirely possible that there are threshold effects, gravitational levels below which certain biological programs fail to activate, above which they function normally, and the threshold might be different for bones, muscles, the heart, the immune system, and the brain. Lunar gravity might be above some of those thresholds and below others. We will not know until humans live at 1/6 G for months or years and are thoroughly monitored throughout. That experiment has never been conducted. It cannot be conducted on Earth. It can only be conducted on the Moon, which means that the first long-duration residents of a lunar base will themselves be the test subjects in an experiment whose outcome is genuinely uncertain. This biological vulnerability intersects with a second fundamental problem that distinguishes the Moon from every other environment humans have inhabited. On the Moon, every element of survival depends on systems that must function correctly every second of every day, and every one of those systems can fail. Consider what a human being needs to survive for a single day. Breathable air with the correct oxygen and nitrogen ratio, carbon dioxide removal, pressure compatible with lung function, temperature between roughly 18 and 26 degrees Celsius, clean water, adequate food, radiation protection, waste management, lighting, communication, medical supplies. On Earth, the planet provides most of these for free. The atmosphere delivers breathable air and pressure. The magnetic field and ozone layer provide radiation protection. The hydrological cycle delivers water. The biosphere produces food. Humans have exploited these planetary services for 300,000 years without building any of them from scratch. Even in extreme terrestrial environments like Antarctica or submarines, the background environment still provides atmosphere, pressure, and radiation protection. The crew always has the option of walking outside and breathing. On the Moon, none of this exists. Every single survival requirement listed above must be provided by engineered systems contained within a sealed pressure vessel. If the oxygen generation system fails, there is no air outside to supplement it. If the carbon dioxide scrubbing system fails, toxic levels accumulate within hours. If the pressure hull is breached, the habitat atmosphere vents to vacuum. If the water recycler fails, the crew begins consuming reserves with no resupply closer than Earth. If the thermal regulation system fails during the lunar night, interior temperatures begin dropping toward negative 170 degrees. If it fails during the lunar day, temperatures begin climbing toward 127 degrees. Every failure is a clock that starts counting down toward an emergency, and every emergency plays out in an environment that offers zero ambient support. This total dependence creates a systems reliability problem of extraordinary difficulty. In engineering, reliability is typically expressed as the probability that a system will function without failure over a given period. A system with a reliability of 99% over 1 year has a 1 in 100 chance of failing during that year. That sounds acceptable until you consider that a crude lunar habitat might contain hundreds of critical subsystems, any one of which could fail in a way that threatens crew survival. If you have 200 independent subsystems, each with 99% annual reliability, the probability that at least one of them fails during a single year is approximately 86%, near certainty. Real engineering deals with this through redundancy, the practice of having backup systems that can take over when primary systems fail. The International Space Station uses this approach extensively. Critical systems like life support, power generation, and attitude control have multiple redundant pathways. If one oxygen generator fails, another can compensate. If one power channel goes down, others carry the load. The station's environmental control and life support system has been through numerous failures and repairs over its 2-decade operational life, each one handled by a combination of onboard spares, crew expertise, and rapid resupply from Earth. That combination has kept the station continuously inhabited since November of 2000, but it works because of where the station is, not because the technology is infallible. On the Moon, every kilogram of redundant equipment must be transported from Earth at a cost that currently runs into tens of thousands of dollars per kilogram for delivery to the lunar surface. Every backup system must be maintained by a crew that is already stretched thin by operational demands. And every piece of redundant hardware is subject to the same thermal cycling, radiation exposure, dust infiltration, and micrometeorite bombardment that threatens primary systems. The supply chain compounds this problem. The International Space Station orbits approximately 400 kilometers above Earth's surface. A resupply mission can reach it within hours of launch. Crew members can return to Earth within hours if an emergency requires evacuation. The Moon is 1,000 times farther away. Resupply missions require approximately 3 days of transit, plus the time required to prepare and launch the mission, which under optimal conditions takes weeks and under realistic conditions takes months. If a critical component fails on a lunar base and no replacement is available on site, the crew must survive with degraded capability until a replacement can be manufactured, launched, transited, and landed. That is not hours. That is weeks at absolute minimum and realistically months. This logistics reality means that a lunar base must carry spare parts and backup equipment sufficient to cover every plausible failure scenario between resupply missions. If resupply occurs every 6 months, the base must carry 6 months of spare capacity for every critical system. Every spare component adds mass to the initial deployment, which adds cost, which limits how much other equipment can be delivered. It is a vicious circle in which every kilogram allocated to safety is a kilogram not allocated to capability, and vice versa. The alternative to resupply dependence is in situ resource utilization, the concept of manufacturing essential materials from local lunar resources. In principle, the Moon offers raw materials that could reduce dependence on Earth. The regolith contains oxygen bound in mineral oxides, roughly 43% by mass. Water ice may exist in permanently shadowed craters near the poles, deposited by cometary impacts over billions of years. Metals including iron, aluminium, and titanium are present in the regolith in various mineral forms. In theory, a sufficiently advanced processing facility could extract oxygen for breathing, water for drinking and radiation shielding, metals for construction, and even produce rocket propellant for return missions. In practice, none of these processes have been demonstrated at operational scale on the lunar surface. Extracting oxygen from regolith requires heating the material to approximately 900 degrees Celsius or treating it with chemical reagents, both of which demand significant energy and specialized equipment. The equipment itself must be designed to operate in vacuum, survive thermal cycling, resist dust contamination, and function reliably for years without the kind of hands-on maintenance that terrestrial chemical plants routinely require. Water ice extraction from permanently shadowed craters presents its own challenges. The craters are among the coldest places in the solar system. Equipment must operate in permanent darkness at temperatures approaching negative 230 degrees. Access to these craters requires traversing terrain that receives no sunlight, which means no solar power for operations, and no thermal energy from the sun to keep equipment warm. The ice may be mixed with regolith in concentrations as low as a few %, requiring enormous volumes of material to be processed for modest water yields. The exact distribution and concentration of water ice remains poorly constrained despite orbital measurements from several missions. NASA's Lunar Reconnaissance Orbiter, India's Chandrayaan missions, and other probes have provided evidence that water ice exists in these regions, but the data describes surface or near-surface signatures. The subsurface distribution, the physical form of the ice, whether it exists as discrete chunks, mixed frost, or thin coatings on regolith grains, and the actual extractable yield per ton of processed material remain uncertain until a surface mission conducts direct sampling and assaying. Plans exist. Hardware is under development. But the gap between orbital detection and industrial extraction is vast, and it cannot be bridged by optimism alone. Even the most optimistic in-situ resource utilization scenarios envision years of development and testing before any process reaches the reliability needed to support human survival. During that development period, the base remains entirely dependent on supplies from Earth. The transition from full Earth dependence to partial self-sufficiency is itself a high-risk engineering challenge, requiring robust fallback capability in case any local production system fails. There is another dimension to the total dependence problem that is less obvious but potentially more dangerous. It is the issue of cascading failure. On the Moon, survival systems are not independent. They are interconnected in ways that create complex failure pathways. Consider a scenario in which the power system experiences a partial failure during the lunar night, reducing available electrical power by 40%. This forces the thermal regulation system to operate at reduced capacity, which causes interior temperatures to drop. The lower temperature reduces the efficiency of the water recycling system, which increases water consumption from reserves. The increased draw on water reserves triggers a rationing protocol that affects food preparation and personal hygiene. The rationing protocol increases psychological stress on the crew, which can lead to errors in judgment that affect operational decisions. A single partial failure in the power system has now degraded thermal management, water recycling, food supply, crew hygiene, crew morale, and operational safety. None of these downstream effects were directly caused by the power failure. They were caused by the interconnected dependence of every system on every other system in a closed environment with no external backup. The International Space Station has experienced cascading failures of this kind. In 2020, a small air leak was detected in the Russian Zvezda module. The leak was initially too small to identify. Over months, the crew conducted extensive diagnostics while the station slowly lost atmosphere, requiring additional nitrogen deliveries from resupply missions. The slow leak consumed crew time, diverted attention from science operations, stressed the air supply system, and created an ongoing background anxiety that affected crew scheduling and mission planning. On the station, this was manageable because resupply was frequent and crew return was always an option. On the Moon, a similar slow leak could not be addressed by simply scheduling an additional nitrogen delivery. It would require identifying and repairing the breach using only materials and tools available on site. In an environment where working on the exterior of a pressurized habitat means conducting a spacewalk on a surface covered in abrasive, electrostatically charged dust under continuous radiation exposure, with no atmosphere to breathe and no acoustic feedback to warn you of secondary problems developing. The system's perspective reveals something about the Moon that the individual hazards, taken one at a time, tend to obscure. Every survival challenge on the Moon is connected to every other survival challenge. Radiation shielding requires mass, which requires either transport from Earth or in situ manufacturing, both of which require power. Power generation during the lunar night requires either nuclear systems, which add radiation concerns, or massive battery banks, which add mass. Dust mitigation requires seals that must withstand thermal cycling that degrades them. Thermal management requires power that competes with life support for allocation. Life support requires water recycling that is threatened by dust contamination. Every solution to one problem introduces constraints, costs, or vulnerabilities that affect every other problem. This interconnection is the reason that a lunar base cannot be designed the way a single-purpose machine is designed. It must be designed as a complete life support ecosystem, closed or nearly closed, with the internal complexity and cross-system dependencies of a small city compressed into the volume of a few pressurized modules. Nothing like this has ever been built and operated beyond low Earth orbit. The International Space Station is the closest analogue, and it relies on frequent resupply, crew rotation every 6 months, the partial radiation shielding of Earth's magnetosphere, the absence of dust, the absence of ground-based thermal cycling, and the possibility of rapid crew evacuation. A lunar base would have none of these advantages. What all of this means, taken together, is that the Moon does not merely present hazards. It presents a system of interlocking hazards that resist piecemeal solutions. You cannot solve the radiation problem without solving the mass delivery problem. You cannot solve the mass delivery problem without solving the power problem. You cannot solve the power problem without solving the thermal problem. You cannot solve any of them without solving the dust problem. And beneath all of them, the low gravity is slowly reshaping the bodies of the crew in ways that no one has ever measured over the timescales that permanent presence would require. What all of this adds up to is not a list of individual dangers. It is a single, integrated reality that anyone proposing permanent human presence on the Moon must confront honestly. Step back now from the individual threats and look at the Moon as a single environment. Not as a list of hazards arranged in sequence, but as one integrated physical reality that a human crew would confront all at once, every day, from the moment they step off the lander to the moment they leave. The vacuum is constant. It does not take breaks. It does not relent during certain seasons. It presses against every seal, every joint, every window, every airlock, every centimetre of pressurized volume, every second of every day, for the entire duration of the mission. It is not a threat that emerges under certain conditions. It is the baseline state of the world. Everything a crew breathes, every molecule of nitrogen and oxygen that keeps their lungs inflated and their blood oxygenated, exists only because an engineered enclosure is holding it against the vacuum's pull. The enclosure must never fail, not once, not partially. A breach of any significant size means the atmosphere starts leaving. There is no recovering it. There is no replacement reservoir in the surrounding environment. The air that escapes is gone. While the vacuum presses inward, the temperature oscillates through a range that would destroy most terrestrial engineering materials within a few cycles if they were not specifically designed to endure it. The habitat's thermal management system must handle this oscillation continuously, rejecting heat during the day and generating heat during the night, switching between these two operational modes every 2 weeks while maintaining interior conditions within a narrow band that human physiology requires. This thermal management system requires power. During the lunar day, solar panels can provide it, assuming they have not been degraded by micrometeorite erosion or obscured by electrostatically adhering dust. During the lunar night, power must come from stored energy or nuclear systems, either of which carries its own mass, cost, and reliability constraints. While the thermal system cycles and the power system switches between sources, radiation is streaming through the habitat walls. Not all of it. Shielding reduces the flux. But unless the habitat is buried under meters of regolith or nestled inside a lava tube, some fraction of galactic cosmic rays and their secondary particles penetrate the structure and pass through the crew's bodies. Every day. Accumulating dose, incrementing cancer risk, potentially degrading cognitive function. And at unpredictable intervals, the sun erupts and the crew must shelter immediately, dropping whatever work they are doing and retreating to a shielded volume until the particle storm passes. This is not a rare contingency. Over a multi-year mission, multiple solar energetic particle events are statistically expected. Each one is an unscheduled operational shutdown that disrupts work schedules, wastes consumables, and reminds the crew that the environment they inhabit is actively trying to harm them. While the radiation accumulates, dust infiltrates. Every surface excursion brings it closer to the habitat interior. Every airlock cycle risks introducing particles that the mitigation systems must capture before they reach air filters, water recyclers, mechanical bearings, and human lungs. The dust does not degrade with time. It does not settle and become inert the way terrestrial dust does when it lands on a shelf. Its electrostatic charge keeps it mobile and adhesive. Its angular geometry keeps it abrasive. Its reactive surface chemistry keeps it chemically active. It is a contaminant that requires active, continuous, energy-consuming management for as long as the base operates. While the dust infiltrates and the radiation accumulates and the thermal system cycles and the vacuum presses, the crew's bodies are quietly adapting to a gravitational environment that provides only 1/6 of the mechanical stimulus their physiology evolved to require. Their bones may be thinning. Their muscle fiber composition may be shifting. Their cardiovascular fitness may be declining. Their immune response may be changing. These processes are slow enough that a 1-week visit would not reveal them, but over months and years they represent a progressive biological departure from the terrestrial baseline that every crew member's body was built to maintain. The crew may feel fine. They may perform their duties capably, but their bodies are changing in ways that will not become fully apparent until they attempt to return to Earth's full gravity, or until a medical emergency on the surface reveals that their physiological reserves have eroded below safe margins. All of this happens simultaneously, not one threat at a time, not in sequence, all at once. The vacuum does not pause while the crew deals with a dust contamination event. The radiation does not stop during the lunar night when power is scarce. The temperature does not moderate during a solar storm when the crew is confined to a shelter. The gravity does not strengthen when a crew member needs to perform emergency maintenance on a failing life support system. Every threat operates on its own timeline, according to its own physics, indifferent to the operational state of the habitat or the physical and psychological condition of the crew. The moon does not negotiate. It does not accommodate. It simply is what it is and always has been. This integrated reality is what separates the moon from every other environment humans have successfully inhabited. Even the most extreme terrestrial environments offer something. Antarctica offers breathable air and atmospheric pressure. The deep ocean provides a continuous medium rather than a vacuum that punishes any failure with explosive decompression. Submarines separate the crew from water, not from nothingness. The station in low Earth orbit, for all its complexity, still benefits from proximity to Earth and the planet's magnetic umbrella. Every analogue that advocates invoke when discussing a lunar base falls short, because none of them combine the moon's specific mixture of threats in the moon's specific configuration of severity, simultaneity, and permanence. Engineers and scientists working on lunar habitation are aware of all of this. They are not naive. The people designing Artemis surface missions, the researchers developing regolith-shielded habitat concepts, the teams working on in-situ resource utilization prototypes, the scientists studying the effects of partial gravity on biological systems, all of them understand the scale of the challenge. The proposed solutions are real. They represent genuine engineering pathways toward extended human presence on the moon. They deserve serious attention and serious investment, but they also deserve honest assessment, which means acknowledging what they have demonstrated and what they have not. Regolith shielding is the most frequently cited solution to the radiation problem. The concept is straightforward. Pile several meters of lunar soil over the habitat to absorb incoming radiation before it reaches the crew. Modelling shows that 2 to 3 meters of regolith reduces the galactic cosmic ray dose by roughly half and provides substantial protection against solar energetic particle events. The physics works. The engineering challenge lies in the execution, moving thousands of tons of granular material in 1/6 gravity in vacuum using equipment that must survive the thermal and dust environment is not a task that any robotic or crewed system has performed on the moon. The closest terrestrial analogue is large-scale earth-moving construction, which relies on diesel engines, hydraulic systems, skilled operators, abundant fuel, breathable air, and a supply chain that can deliver replacement parts within hours. None of those conditions exist on the lunar surface. Autonomous robotic construction is one proposed approach, sending machines ahead of the crew to prepare a shielded habitat before humans arrive. This is a promising concept that multiple space agencies and private companies are actively studying, with prototype rovers and excavation systems under development in several countries. But it requires reliable autonomous operation in an environment where dust clogs, mechanisms, thermal cycling fatigues components, and a round-trip communication delay of roughly 2.5 seconds makes real-time teleoperating from Earth difficult and slow. No robotic system has demonstrated this capability on the Moon. Lava tube habitats represent another compelling concept. The Moon's surface preserves ancient volcanic features including collapsed lava tubes, tunnel-like voids formed when flowing lava crusted over and then drained away billions of years ago. Orbital observations have identified candidate skylights, holes in the ceiling of collapsed tube sections that suggest extensive subsurface voids. Some of these voids may be tens of meters in diameter and hundreds of meters long. A habitat placed inside a lava tube would enjoy natural shielding from radiation, micrometeorites, and the extreme thermal cycling of the surface. The temperature inside a lava tube, insulated by meters of solid rock, is expected to be relatively stable at roughly -20 degrees Celsius, still cold, but far more manageable than the surface extremes. The concept is elegant. The reality is that no mission has ever entered a lunar lava tube. No one has measured the structural integrity of these voids. No one has confirmed that the floors are stable enough to support a habitat. No one has assessed the dust environment inside a tube or determined whether the confined geometry creates problems for communications, access, or emergency egress that surface sites would not present. Lava tubes may prove to be an excellent solution. They may also prove to be inaccessible, structurally unsound, or operationally impractical. The data required to distinguish between these outcomes does not yet exist. Three-dimensional printing with regolith is another concept that receives enthusiastic attention in architectural and engineering studies. The idea is to use the abundant raw material of the lunar surface as feedstock for additive manufacturing, building habitat walls, landing pads, roads, and other infrastructure directly from local material. Several research groups have demonstrated sintering of regolith simulants using concentrated solar energy or microwave heating, producing solid blocks or structural elements in laboratory conditions on Earth. The European Space Agency has partnered with architectural firms to produce prototype structures using simulated lunar soil. Some of these demonstrations have produced impressive results. Walls and domes with structural integrity comparable to terrestrial concrete. The technology is real and advancing, but scaling it to the point where a printer can autonomously construct a multi-room, pressure-tight, radiation-shielded habitat on the lunar surface is a fundamentally different proposition from producing sample blocks in a terrestrial lab. The printer must operate in vacuum. It must manage thermal extremes that cause the feedstock to behave differently than it does in a climate-controlled laboratory. It must handle feedstock that is electrostatically charged, abrasive, and variable in composition depending on where it was excavated. It must produce structures that can hold atmosphere against vacuum without leaking through microscopic cracks or pores in the printed material. The structure must then be fitted with airlocks, windows, utility penetrations, and connections to life support systems, none of which can be printed from regolith. No three-dimensional printing system has been tested on the lunar surface. The gap between laboratory demonstration and operational deployment on the Moon is wide, and closing it will require years of robotic precursor missions and iterative testing under actual lunar conditions. Nuclear power systems, particularly small fission reactors, offer the most credible solution to the lunar night power problem. A fission reactor does not depend on sunlight. It can operate continuously for years, providing steady electrical power and potentially waste heat for thermal management. NASA's Kilo Power project and its successor efforts have produced promising test results on Earth. The technology is mature compared to many other proposed lunar systems, but deploying a nuclear reactor on the lunar surface introduces unique constraints. The reactor must be positioned far enough from the habitat to limit crew radiation exposure from its own operation, or heavily shielded, which adds mass. It must be launched from Earth, which involves regulatory, safety, and political processes that add time and complexity. It must survive the landing, the thermal environment, and the dust environment without compromising the integrity of its containment or cooling systems. Multiple units would be needed for redundancy, because a single reactor base with no solar backup during the lunar night has no margin for reactor failure. None of this is impossible. All of it is challenging, and none of it has been demonstrated operationally on the Moon. The common thread linking every proposed solution is the distance between concept and validated capability. Regolith shielding works in physics models. Lava tubes exist in orbital imagery. Three-dimensional printing works in Earth-based laboratories. Nuclear power works in terrestrial test facilities. Each of these technologies addresses a genuine problem with a genuine engineering approach. None of them has been proven in the integrated, hostile, unforgiving environment of the actual lunar surface, where every system must function not in isolation but alongside every other system, under simultaneous attack from every environmental factor we have examined. This is not an argument against pursuing these technologies. It is an argument for understanding where we stand. We are not on the verge of building a lunar base. We are on the verge of beginning the process of validating the technologies that could eventually make a lunar base possible. That distinction matters because the public conversation about the Moon often conflates aspiration with capability, treating architectural renderings and concept studies as though they were construction plans, awaiting only a budget allocation. The reality is that decades of engineering development, robotic precursor missions, and incremental validation separate today's concepts from a permanently crewed lunar facility. Consider the Artemis program itself as a measure of where we stand. Artemis 1 flew an uncrewed Orion capsule around the Moon in late 2022. Artemis 2, which returned just days ago, carried 4 astronauts on a lunar flyby without landing. Artemis 3, planned for mid-2027, will test lander rendezvous and docking in Earth orbit. Artemis 4, if it proceeds as planned in early 2028, will attempt the first crewed landing since Apollo 17 in 1972. If that landing succeeds, 2 astronauts will spend approximately 1 week on the surface. 1 week. More than half a century after Apollo, with vastly more advanced technology and decades of accumulated spaceflight experience, the planned return to the Moon targets a surface, stay roughly comparable in duration to the longest missions we accomplished in the early 1970s. The program is advancing. The engineering is real. But the pace reflects the genuine difficulty of what is being attempted, not bureaucratic timidity. The cancellation of the Lunar Gateway earlier this year further illustrates the distance between ambition and execution. Even an orbital platform designed to support surface operations could not survive the program's resource constraints. When something had to give, the station gave way to prioritize the landing itself. The path from a 1-week surface visit to a permanent base has become longer, not shorter. None of this means that humanity should abandon the Moon. The Moon is scientifically valuable. It preserves a record of the solar system's early history that Earth's geological activity has long since erased. The ancient impact basins and exposed crustal material contain information about the bombardment environment that shaped the inner solar system during its first billion years. Its far side offers a radio-quiet environment for astronomy that no terrestrial site can match, shielded from Earth's electromagnetic noise by the entire bulk of the Moon itself. Its polar regions may contain water ice that could support future operations and serve as a resource for deep space missions beyond the Moon. Understanding how humans function in partial gravity is essential for any future mission to Mars, where gravity is roughly 3/8 of Earth's, and where the consequences of physiological deconditioning would be compounded by a return journey lasting months rather than days. The Moon is the nearest laboratory in which that question can be studied under real conditions rather than simulated ones. If water ice proves extractable at useful volumes, it could also serve as a source of rocket propellant, potentially reducing the cost of missions deeper into the solar system. These are legitimate reasons to go. They justify the investment. They justify the risk. But they do not justify pretending the moon is something it is not. And what the moon is not, above all else, is a place that gives anything away. This is the central truth that everything we have covered has been building toward. The moon does not provide air, pressure, shielding, thermal regulation, food, or accessible water at the surface. It does not provide protection from radiation, dust, or hypervelocity impacts. It does not provide sufficient gravity to maintain the human body in its evolved configuration. It does not provide a magnetic field, an ozone layer, a medium for sound, a weather system, or a biosphere to recycle waste gas into breathable air. It provides none of the planetary services that Earth delivers continuously, silently, and at no charge to every organism on its surface. Every single thing a human being needs to survive on the moon must be engineered, built, transported, installed, powered, maintained, repaired, and defended against an environment that works ceaselessly to degrade, erode, contaminate, irradiate, and thermally stress every component of every system. This is not a temporary challenge that will ease as technology improves. The moon's vacuum will not fill, its temperature will not moderate, its radiation will not diminish, its dust will not soften, its gravity will not strengthen. The environment is fixed. It is the technology that must evolve, and it must evolve to a level of reliability, autonomy, and self-sufficiency that no human system has ever achieved in any environment, terrestrial or otherwise. This is what makes the moon fundamentally different from any frontier humans have previously crossed. When our ancestors migrated out of Africa, they found new climates, new terrain, new challenges, but they always found air to breathe, water to drink, ground to walk on, and food to hunt or gather. When Europeans crossed the Atlantic, they found a continent with breathable atmosphere, drinkable rivers, arable soil, and forests full of game. When explorers reached the poles, they found conditions that were brutal but survivable with sufficient preparation, and they could always retreat to more hospitable latitudes. Even the deep ocean, arguably the most alien environment humans have entered, provides a continuous medium that surrounds and pressurizes the vessel, and the journey home is measured in hours of ascent. The moon provides none of this. It is not a new continent waiting to be settled. It is not a harsh frontier that rewards those tough enough to endure it. It is a world that is fundamentally incompatible with unprotected human existence, and that incompatibility does not diminish with familiarity or experience. An astronaut who has lived on the moon for 5 years is exactly as dependent on their life support systems as an astronaut who arrived 5 minutes ago. The environment does not become less hostile. The technology does not become less critical. The margin for error does not increase. If anything, it decreases. As equipment ages, consumables deplete, and the cumulative effects of radiation, dust, and thermal cycling erode the margins that engineers built into the original design. There is a phrase that engineers use when discussing systems that must function perfectly and continuously to prevent catastrophe. They call them zero-fault tolerance systems, and the moon demands them. A zero-fault tolerance system is one where a single failure leads directly to loss of mission or loss of life, with no intermediate state that allows recovery. On Earth, very few systems operate this way because the environment provides fallback options. A building that loses its heating system in winter is uncomfortable but survivable because the outside air, while cold, is still breathable and the temperature is still compatible with human life. A hospital that loses power switches to generators, and if those fail, patients can be evacuated to another facility. On the moon, the entire habitat is a zero-fault tolerance system with respect to pressure integrity. A breach that exceeds the capacity of the atmospheric supply system to compensate is not an inconvenience. It is a life-threatening emergency with minutes of margin, and unlike a terrestrial emergency, there is no external emergency response. No fire department arrives, No rescue helicopter is dispatched. No neighboring facility opens its doors. The crew must identify the breach, locate its source, and repair it using only the tools, materials, and skills available inside their own pressurized volume, while wearing emergency breathing equipment, while the atmosphere they depend on leaks into the void outside. This zero-fault tolerance applies not just to dramatic failures like hull breaches, but to the slow, grinding attrition that the environment imposes on every system. A seal that is 99% effective at excluding dust is still emitting 1% of the dust that contacts it. Over months, that 1% accumulates. Over years, it degrades the systems it contaminates. The failure may not be sudden. It may be the kind of gradual deterioration that only becomes apparent when a system is needed at full capacity during an emergency and delivers less than expected. The moon, then, is not simply a dangerous place. Many places are dangerous. The moon is a place that requires perfection. Continuous, sustained, uninterrupted perfection in the design, construction, deployment, operation, and maintenance of every system that stands between a human crew and death. And perfection is not something that engineering delivers. Engineering delivers reliability. It delivers redundancy. It delivers margins of safety that can absorb expected variations and foreseeable failures. But it does not deliver perfection, because materials fatigue, components wear, software encounters unforeseen states, and humans make mistakes. The gap between the reliability that engineering can provide and the perfection that the moon demands is the space in which every lunar habitation effort must operate. Narrowing that gap is the work of decades. It is the work that Artemis is beginning. It is the work that every robotic precursor mission, every technology demonstration, every material science experiment, and every biological study of partial gravity effects contributes to. The harsh truth is not that the moon is hostile. Anyone who has studied the lunar environment for more than a few minutes already knows that. The harsh truth is that the moon is hostile in a way that offers no natural compensation, no ambient safety net, no environmental grace. It does not reward courage. It does not yield to persistence. It does not soften over time. It simply presents its conditions every minute of every day and waits for the technology to match them. If the technology matches, humans can survive there. If it falls short by any margin in any system for any duration longer than the backup capacity can cover, the moon will do what it has always done to unprotected matter on its surface. It will irradiate it, bake it, freeze it, blast it with microscopic projectiles, coat it in clinging abrasive dust, and leave it sitting in silence, in vacuum, under a sky that is always black. That is the moon, not the moon of poetry or mythology or childhood wonder, the physical moon, the real one, the one that Artemis II just circled at 4,000 miles and came home from without landing, the one that 12 human beings touched briefly, decades ago, and then left, the one that every nation with a space program speaks of returning to, as though return were the hard part. Return is the easy part. We have demonstrated return. What we have not demonstrated, and what no one has yet demonstrated, is staying. The moon is 239,000 miles away. You can see it tonight. It looks close. It looks peaceful. It looks like a place you could go. And in a sense, you can. You can go there the way Apollo went, the way Artemis is going. You can visit. You can collect samples. You can plant instruments and photograph the view and fly home and tell the story. But living there, building there, raising the first generation of human beings who call the moon home, that is a different undertaking entirely. It is not a journey to a destination. It is a confrontation with an environment that provides nothing and demands everything. It is the most difficult sustained engineering challenge our species has ever contemplated. Not because any single problem is unsolvable, but because every problem must be solved simultaneously, sustainably, and without interruption on a world that will never, not once, not ever meet you halfway. That is the harsh truth about how hostile the moon really is. And understanding it is not the end of the conversation about going. It is where the real conversation begins.